So today, since we are basically focusing on the radar-centric research, so he is going to talk about VHF, UHF, radar signal processing. You do experiment in some way, you collect data, how do you process data, and so that you can get the atmospheric parameters. Okay. So this is what actually he is going to speak. Okay. So I invite Dr. Anandan to deliver his talk. Okay. And he has written also a lot of papers on signal processing, including the higher order spectral estimation. Somebody was talking denoising, noise reduction and things like that. I think if you have a question, you can ask him. Okay. Thank you.
Yeah, very good afternoon to all of you. I hope you people won't sleep. If you are sleeping, I will also sleep very soon, because very heavy lunch is provided by professor, and I have taken more sweet also. That is what my problem now. Anyway, good that introduction is given by Dr. Durga Rao about the systems and how MS radar is basically looks for the atmosphere and what we are, why the design is should be like that. I will just extend this talk. Some of the slides may be repetitive in nature to continuity to form that point, and from that probably I may skip also some of this because I don't know the way that it is going to presentations was the, so that I also kept it for some understanding of that one. Nevertheless, don't worry about it. As you all of you know, that one signal processing is a subject more on mathematical oriented, as well as sometimes will not grasp very fast on that point. Doesn't matter, it is simple in nature. That's what I try to explain, how it is changes the signal extractions and how you get the signal by doing such and such terms. Probably you heard about filters and other things, what is importance from that point. So this is the diagram, same diagram what Dr. Durga Rao was putting it, but I am very simplifying it. Anything when you are talking about it, about a radar, this is a total radar. Very simple nature, you can look inside. It starts from pulse modulator, frequency synthesizer. I have written everything which is how you will decode your signals, which is transmitted, put it back, and it is coming in your hand, what you are looking for it. Finally, what you say about it, you will get it, basically the signal which is mainly to your Doppler shifted signal. Doppler shifted means what is transmitter frequency, it gets shifted due to the activities what is it is encountered while it is passing through it and reflected back. That's what the most important. So here you look, there is a starting from frequency synthesizer. It's a radar point of view. I am not going into general radar. Any radar when you take it, these are the blocks. And these blocks changes, internally changes, depends upon the explanations what is given in the last time, that what are you looking, how you will process that one, and accordingly that circuit is changing it and it is extracted. But otherwise, all radars looks like same. That's what is a fundamental nature. So you can see here a frequency synthesizer. It's a very stable continuous wave generations model, and which is basically locks all the systems to a fundamental frequency. That is what we call it as a coherent radar. So from that point, we will have signals, and it is having a pulse modulator also part of it. What it means actually, you have a signal F1 stylo, which is a stable coherent oscillator, which will probably you people are learning it. Then it is combined with some of the signal, additional signal, which is we call it as IF frequency, intermediate frequency, combines that one and goes to the transmitter. So that is the point at which we are seeing it. Transmitter is there. Finally, it will come to TR switch. That is nothing but it is explained as a duplexer or whatever it is model. It will just convert it, get back. You can look inside a simplified form of the diagram where it is coming to finally transmits. You are transmitting to an antenna. You get into your waves are passed to the free atmosphere and waiting for the return to come inside. All this thing is written, and what finally we are looking for is a Doppler frequency shift is to be extracted. How do we extract that? So transmit receive switch, once it transmit, it will come back into receive path. So receive path, you can see same thing is happening. You have an RF amplifier, because very low level signal is coming, you have to immediately, we call it as a low noise amplifier, LNA or something like that. So that is very essential for the system, and that brings the signal. Then we have to do the reverse process, what you have done the transmit time. Transmit time, we mix the two signals. It's a stable oscillator what is generated is a shallow signal, and the coherent oscillator also generates its IF frequency which is transmitted. But along with it, you got back one more component, which is what your characteristics of the atmosphere. That's what we are trying to extract it here. So when you talk this part, you can see here a simple explanations. You are sending it signals, RF signal, which is now all phase shifted, and you got it. The frequency, which is F1 and F2, what you transmitted along with some component, which is a characteristic shift of the atmosphere, and there is a phase also will get changed along with when it is transmit path is happening. These are all important character. When an electromagnetic signals, when it goes, basically amplitude, phase is the most important point, which has to be looked back when it is coming. And that will characterize what is the medium you are observing it. This is what, as simple as that, you can explain how your electromagnetic signals can give the information about the atmosphere or any target you are observing it. So this is all about it. What you say, do it, a signal is there, and when you are again multiplying with signals with yellow, B signal, and simple mathematics, you look inside, what you learned in mathematics, sine alpha, there are two components, one is alpha, sine beta, you know that one, it is, once you do it, you can decompose into two components. Same thing, you are demodulating, you are bringing up the signals into two parts, and the higher part is having F1 plus F2 plus FD, lower part is reduced to F2 plus FD. F2 is some IF signal is mixed, and FD is that one. Now finally, you have to get FD again. This is what all about it. So we will do again mixing with some signal, which is used in the transmission type. Again mix it in the second stage. You are getting again higher component as well as lower component. Very higher order components, we will not keep it here. All these things will be filtered out. So the filter is coming in actions to take out this signal. Finally, we will get only one component, which is corresponds to what we talk about. This is all talks of, we are looking back into your radar principles. So this talks about the velocity, how you extract all the components. Every time that you can see that the block is getting shifted the color where it is getting actions. So once you got VID, the Doppler shifted signal, or you can take the IF signal also directly, or you can take, in the present case, the new generation systems are coming, straight away your carrier plus F1 plus F2 plus D is digitized. Analog to digital converter comes for the analog signal making into digital domain. So that is what all about your system point of view. After that one, now my topic is coming with the digitization and its problems, or how to resolve or how to get back the desired signals. We can do signal processing in various ways. Earlier days we do that because lot of things computer cannot do it, or computer is not fast enough to do it. So we will try to implement everything in the hardware itself, and there is a programmability also introduced in hardware, either with ASICs, FPGA or DSP chips are available, or microprocessor can do it, because it works almost like that. Almost in principle of real time, because we need to get the data without losing it. We have to do everything in real time. But in modern systems, most of the, if this kind of system we want to design, it can be done as soon as ADC gives the digital data, computer can do the back-end processings. Quite fast computers are available. It is not like olden days what we have done it or what we are implemented in the previous systems. So this is all about it. We will have an observation point. This you can see tomorrow also when you are coming there. You will have an observations of the raw data. That means nothing but a video signal that you can see in oscilloscope. And the data signal is what they basically that scientists look for it to extract the further final information about the atmosphere or atmospheric characteristics or changes, whatever they are looking inside. So many things you can study it, and how do you study about it. So basically radar equations when you are looking, this is explained in a short in the previous slide, but there are two targets. One is the soft targets. Soft targets is normally plates with the volume scattering. Volume scattering, which we are talking about, the refractive index changes basically influences or gives back the scatterers. Whereas point target, you can see it is a scattering cross section, because it's having a specific shapes and dimensions that will determines what is the scattering back to that signal. So actually when it is looking in this hard target, the intensity or the reflected signal or the wave which is passes through the atmosphere, it undergoes the path loss at the rate of r⁴. Whereas when we consider into volume scattering, it is reduces by square of it only. That is one advantage we get it. But definitely when you look into volume scattering, the scatterers are gives very low signals, return signal or back scattering is very, very low. So that is why we need very high power systems and as well as large area array of process, basically to talk about the multiplied values of the power and things. So look into the problems now. What we get it, actually when you are doing it, everything is not, this is a programmable device in front of you. Radar is, you are not designing the radar, but all radar parameters for the observations, it comes through your radar controller as an observational terminal and you can program it. Tomorrow you are going to see that some of the experience when people are setting it, you can parameters, you can set it accordingly, observations will be changing it. So that is what important, but when you are setting the all these observations, you must know some of the things that each is having its own impact on the observational regions, what you are looking about it. This is what I'll talk about it. We want in high temporal resolutions, the observation is conducting what is one of the factor which is used for, because this is the SNR, signal to noise ratio, which matters to us that when we are detecting the correct signal. So for that one, these are the equations which or the parameters which comes influencing your overall observations time. As far as the radar is concerned, I am not talking about the atmosphere per se, anything you are observing it, these parameters comes in effect for your setting the values to get a return. Irrespective of you are taking this or not, or the atmospheric science or no, even though we are vouching for you, people all should join for the atmospheric research and the program. That's what director is telling me that we should get maximum number of people to come into the domain. So I am vouching for it. Irrespective of this one, you look simply probably you take a commercial job for radar design itself tomorrow. But this situation is same. So opportunity exists here also in a wider way because atmosphere is very big. Probably you can say 20 trillion volume of kilometer volume is exists in this space to look into it. So your observational region is very big. Compared to a small domain in a company, you work on that one and do a small problem. Problems are much, much bigger here and going to grow day by day because man-made problems are creating further atmosphere and space is getting into trouble. So we need an instrument, we need people to look inside and corrective steps like if people are talking about policy decisions and all, but observation is very important and create a situation saying that these are the things we are doing good, these are the things we are doing bad. So somebody has to watch that also. We need good people to come inside and do research in this area also and really showcase that what is really happening. And India has to grow in that direction also very nicely. That's what because this is equations, don't worry about it. When he is going for a tutorial class, probably you will be learning more in the intricacies of each and everything. That's what I am skipping it and going for so many other things because each one is important to you for the observation point of view. Each equation, same equation, I am playing with the small variations in the change, what its impact in the observational area. This is what important to understand. Yeah. So as you know that when a range goes, because your signal gets weakened, so that is also important point. So finally, you are getting into weather observations, Cn square matters to you, Cn square also reduces as the height increases, so that reflectivity comes down. When the reflectivity comes down, your SNR goes down, so detectability goes out. So that's all about it, about the basic system parameter design, start from Cn square. As a radar designer, I should have the value of Cn square and get back into various other parameters where the user scientist determines that what temporal resolution I want it, what space resolution I want it, that determines that how do I design a radar basically back into the calculations. So very simple mathematics, back into the look inside, and that is what radar designs. You have to match to these conditions, bring the blocks properly, see that everything, there is no contaminated signal, there is no higher order spectral or the frequency components are coming inside because the signals what we are looking very, very low. Probably what you transmit, say 1 million, you are getting 1/1000th of that power back to you, you have to extract it back. That's what the concern about a signal processing person. How do you extract such a low level signal without getting contaminated by the noise around it and at the same time and make sure that that detection is correct, otherwise you are doing a lot of errors or your interpretations in the scientific arena is getting lost. So the essence of, now we are coming back to the, once you got a time domain analysis or time digitized signal is there, which is in the time series data. Again we will go into processings. Frequency analysis is normally or Fourier domain is being used. So from there we are trying to get the best signal out of it. So what is the essence is, how well the assumed signal model represents the data, because these are all probably it is clicking you back into your curriculum when you are learning it. Look inside that one, what your theory you are learning it, either in the frequency domain, time series analysis, or Fourier transforms, or various transforms you are studying in your curriculum very soon. Or maybe it is already undergone that test. So you can look inside, that all matters here, back into your calculations. You should be very careful what you are learning inside. Don't just leave it, because it is going to catch you back when you are getting into the any field of studies or when you are going to interpret with any signals. So that's what, it is not specific to atmospheric signal, it is holds good for any signal analysis, how you do it, because if I go into theory side, frequency domain analysis, everything is an approximations. People will say that ideally I recreated the original signal. No, you cannot touch or call that one the signal is created back. You are only approximated to the original signal, because signal is lost its real ideal conditions, because it has gone through some numerical analysis or numerical computations and you are bringing into it. But it is what is said, assumed signal model, what it represents the data, you are happy with these situations and you can do it. So these are the following conditions which has to be applied. Then we are looking for, I was talking about the signal detection and its importance. So we are morning they are talking about that pulse compression techniques, which is essentially required because you want a very high resolution data, observations of very high resolution. At the same time, you have to detect at the long range. So we use pulse compressions and all these things. So let me skip all these things because it all matters to you that how you get the best signal out of it. That is what the point at which the discussion is coming. So what we do, pulse compressions, you can see some glimpse of that one, because probably somebody maybe learned or heard about Barker codes or some compression techniques. Why it is important from the point that signal which extracts, or because anything which you create and it is basically what it happens, it convolves to the medium that you are going to face it. So convolution always is not straightforward. It will always create small babies around it. So that is what is happening here also. When you send a small code which is having a shape of like that what you are seeing in the rectangular pulse, and when you correlate with the or the convolve with the medium and you want to decode it back, probably that signal will be shaped out in this model, last one what you are seeing it. That means it is not ideally you got a single line. Well, you will get a smaller, so many points. These are all in the written in the time series, but effectively it is time is nothing but range of observations. So the signal which is supposed to come inside is get leaked into the adjacent range gate. So you have to take that also is one of the important. So opportunity exists now. So you can look inside what you learned. Probably different codes are available, and different codes you are studying as part of your signal processing course, or some coding techniques or something, but you can make use of it in the system. You look that one, another code is coming here, which is, we call it as a complementary codes. Normally what is the shape of that code? Two codes are complements to each other, right? You will never thought that one where I will apply this, and what is its importance? You see that one, atmospheric radars of this kind, we need a very high, very low signal to be boosted back. So we will use such kind of techniques that, and at the same time leakage to the adjacent range gate should be as low as possible. So you sum it up these two things. I am instead of getting so many small babies around it, I am getting a single pulse. So two stream of pulse goes one after the other. Take that two streams back, decode it, add it together, you are getting the desired result. This is what we do it. So it is nothing free in that sense that what we are doing it with some concern also. So essentially when I am using say a 500 Hz transmission is done with a repetitions of 500 Hz, I add it together two pulses. Effectively the frequency of bandwidth or the time of time is added 2 times. Essentially I will reduce my bandwidth of observations to 250 Hz. That is one point which has to be remembered when I am doing this kind of things. Okay, go to next. So these are the total blocks which comes in the signal processing area. I will not take to any questions. I will just orally go here itself, so that We do the decoding. Once you transmitted in a pulse is coded form is transmitted, we have to retrieve the information. That is what we call decoding of the signals. Then we do coherent integrations. That's nothing but a gain introduced in this system by oversampled signal reduces its samples by adding adjacent, so many repeated signals will be added together and make a single point. What is the effect of that one? We are actually filtering the signal also. The effectively, suppose we have a 1000 Hertz signal, 1000 Hertz component, I add it 10 times, it becomes a component of 100 Hertz. But at the same time, suppose if I am putting 100 Hertz, I should make sure that one, my FD, which is the first point which I raised, the Doppler shift which is happening on my carrier signal, should be inside 100 Hertz. That is the point you have to remember. That is what it is, the wisdom has to go inside when you are doing an experiment with the radar. What I am doing, what are the impact on my observations, whether it is sufficient or not, or can be used or not, you have to have a judgment. This is very important when you are using radar. This is the final stage. Design of the radar, I am not talking about it. I am talking about it. Usage of radar for your particular experiment. You should be careful about these various parameters. What is its impact when I am conducting some particular experiment? This is to be taken care. I am little fast. I am sorry for that one because we have to keep it in time for some extent, but still I will be riding out of my time, but because I have so many slides to run in a different subject, so that's what I am going inside. Next one is a normalization. Why normalizations? Because you see that one, you will be conducting experiments at a different time, different date with the different parameters. Atmosphere need not be changed. But when you conduct a different observational parameters inside, for example, coherent integration is changed. For example, you are introduced a pulse width, a bigger pulse width to get the return back. But atmospheric returns are supposed to be the same if the condition is not changed in the atmosphere. So you have to, but the return signal strength is modified or changed because of your observational parameters are getting changed. So you should do a basic justice to the signal, that one, it is taken care in a common platform. That is what we call normalization has to be done at various extent. Hardware also sometimes will change. Suppose ADC is changing from 14-bit to 16-bit when you are after 5 years or 10 years of the radar operation, you will be going for a latest hardware. That time also it is an important fact that you see that one, your signal, you may be, because now talking about data mining, you have taken the signal of the 10 years back and you compare with the present 10 years. It is required because we have to understand that one, how the atmosphere is changed. The signal data mining will tell you that one, what way the signal is changed, but you should not wrongly interpret because of your observation parameters is there wrong, or you kept it something there and now presently you are capable of doing something more and you had kept it there and it is not normalized, your observation may not be correct. So that normalization is very important from that point. Next one is windowing, because normally anything happens in this world, there is a windowing. You don't have a data of, any long series of data which you can essentially, because anything which is asking you, it need an infinite number of, because a Fourier series, if you are looking also, you see that one Fourier series ideally can be minus infinity to integral of minus infinity to plus infinity of x of t into x of x. That means you have to have ideally an infinite series to represent your time series data into frequency domain. In exactly you want to reproduce, but that is not possible in the world. You will be always short of time, you will be contained with the whatever data is there and you are approximate to that model. That is what my slides say, that one, you are almost a modeling to a real situations, but you are not doing the real data analysis. But model is sufficient to you, depends upon the situation where you are looking, that determines that one, is it okay or not. That is your judgment. You have to learn that process. Is it I am doing justice to my signal analysis for a given situations. That determines it's okay. Then we do Fourier analysis. Then one more integration is done. Once you do Fourier analysis and power spectrum, if you add the signal of power spectrum, it is called incoherent integration, because by the time the phase information of the signal is lost, that is why we call it as incoherent. Whereas the first one is written as a coherent integrations, where that signal phase is kept as intact. When it's incoherent integration, power spectrum is taken, power spectrum is lost its phase information. So when you are adding it, it is called an incoherent integration. Both is having different gain. Again, signal processing parameter is coming inside, what you should do it and when you are supposed to do the signals. So that is one thing. Then we do spectrum cleaning. Whatever you get, it need not be good. It has to be cleaned properly. Then we go for the noise level estimation, because whatever you receive through the receiver, it contains all type of noise. And it will create a base noise floor fluctuations, or that one you will have a small signal component. So you have to do a noise level estimations and bring the signal down, extract the signal out of it. Then we do the basic parameters from the atmosphere, which we call the moments data. Moments data is nothing but your signal, electromagnetic signals what you see, you are basically looking for the reflectivity, the power of the signal returned back to you. Then you are looking what is the shift is happened on the frequency composition. So we call it FD. And again that one, what are the variances happening on that FD itself, because FD need not be, when an ideal case what you are expecting, only one shift, one line, right, in the frequency composition. But that will never happen in this spectral analysis. You will have a spectrum of signals which is coming out and an envelope will be created. You can see that signal also after some time. Okay, what I already explained to you, let me skip here. So this is the signal. Essentially when you look your original signal, suppose if it don't have an integrations, when I am integrating something, you can see that noise fluctuations are getting reduced. The overall this timestamp is slightly different. It is actually 64 milliseconds is the total timestamp. Here it is only plotting 15 milliseconds. So that is the difference, because it has taken time scale, there is a mistake there. So what you can see, essentially what we want to show, when you do coherent integration, purity of the signal is bringing back and your uncertainty in the determination is reduced. And this is how in the spectral domain it looks like. So earlier it is having lot of fluctuations, and finally when you look in the signals, you have less number of fluctuations and detection is much better. This is part of the coherent integrations. We talked about Fourier analysis and how the spectrum is coming out. So let me come out here. So various signal forms, and incoherent integration also improves your detectability or the basically signal to noise ratio on the signal, and by that way that you can improve your signal. So let me skip here also. You have signal with clutters or the unwanted signal in between, so you have to remove the signal. That's what we call your spectrum cleaning process. So that various methods we can use it for the noise removal. I just gives you a glance that one, because so many activity happens around with the signal, but opportunity is there to look inside that one. Still opportunity is there that how you can get the best signal out of it. So many things are we are doing it in back end, and these are all established, and it is clearly shows the results how we can bring it out. So that's a noise. And finally what I talking about, that moments estimations, zeroth power. What you are seeing, zeroth power is actually, it is nothing but the spectrum is calculated, the spectrum envelope, what is the energy content available, you are just trying to get back that signals. And we have another method also, actually not only in the time frequency domain what we analyze, we can do it with the time based analysis, what we call as pulse pair techniques. That means it is nothing but a correlation method of the two signals, which comes originally in your hand. You can do a pulse pair computations and retrieve the same information what we retrieve through the Fourier based method. So that's what the signal processing part of it. So we will get the same informations what we are talking about, it signal total return signal power, its velocity component, that means Doppler shift, and its variance. You can take the second file. Finally, we talk about that one. After all this process is over, we extracted the signal. Now estimation technique starts, because so far it is all the return signal. How do you extract the informations and keep it ready? Now we are talking about the velocity is the most important component. From these atmospheric signals, we look for the three-dimensional velocity. So three-dimensional velocity, how do we extract? So There are two methods which is discussed partially in the first presentations. We call it as Doppler swinging method, transmitting in 3 different directions anywhere in the plane, and you can get the radial velocity from that component. From there you can derive the horizontal component at each interval what you are aiming to get it. And there is another method which is called space antenna, in which there is no beam swinging, or the not looking at the different directions, the transmission is not happening. We will just transmit vertically 3 sections or 3 group of arrays of antenna. That way also you can extract the wind information. Third method will be discussed little later, which is almost the same as into second form, space antenna method, but it is having slightly different because we are forming the beams in a different angle. That will be touched upon. What it does basically, it is in a Doppler beam swinging, you are tilting the beam into different directions or the radiating in different directions from the off zenith, and we retrieve the information like what we are explained so far and get it. Whereas in the space antenna techniques, you are transmitting in a single point, then receive through 3 sections, 3 groups, and from there also you can, drift velocity can be calculated and you can retrieve the informations. So this is the method. Normally we will get from the any radar or the wind profiler systems, basically wind vector, reflected radio wave, and this is the basic, it is calculating that basic airflow or the whatever wind is you are trying to get it. So just how we can extract the informations, just small mathematics inside. We are basically getting a phase shift or a phase changes, nothing but it is simply for your understanding level, I just kept it. You are getting a signal and it is nothing but an omega t, which is a function of 2 pi ft. It is f can be converted into c by lambda, and r it is nothing but in t, in terms of t, r by lambda. And you put it in a 2-way, it is a 2 times. Finally phi t is nothing but these compositions, and d phi over dt is the rate of change of the phase, which determines your velocity composition. So we will get something like the simple calculation, and finally fd is nothing but 2v by lambda, or v is equal to lambda into fd by 2. It's a very simple mathematics, where that this is what you are extracting it, and this is what you are looking from the phase change which is happening in your electromagnetic wave what you transmitted. Your velocity is in your hand now. You can do further studies of the atmospheric research. So till to this one, actually it is already explained last slide, but it is a little goes inside how you get these components. But normally when we do, it's sufficient that to get radial velocity of any directions, 2 directions, you put a proper angle of information inside, you can extract the winds. But we do little more inside because system is capable of getting multiple beams in a different directions. So you can do a linear estimations on the top of it, trying to see that when so many equations are available, your residue will be reduced as much as possible, right? So that is what the principle is employed here. If you have more number of beams, your error in estimations are reduced. This is simple signal processing. In anywhere you do it, it is the same principle, because the more the number of sample points, more the number of the equations are you are deriving it. Final equations, your error will be reduced. This is what simple as that. So you get it finally, your wind velocity or the speed and directions, and comes out of it. Coming to space antenna drift, actually it is transmitted, as you say that one pictorially, you will be transmitting with a single middle of the sections, and 3 different segments will be there to receive it. From there you can again extract the informations. Okay, it is what we call as a full correlation analysis. Basically, you know, you heard about correlations. Correlations and cross correlations all are studied factors in various statistical properties, right? So that will tell you that on how to derive it. I am not going to details to that point because it is little involved mathematics, where that you are getting a correlation coefficients of various segments. You have a triangle now, easily shown earlier. I don't know whether it is there now. Yeah, I will come to, yeah, you have 3 points here. You can look inside that one. If I can create in an array, this is almost like what you have in the now ST radar here. You can create 25 channel systems, which is I am just discussing here, so that you can create different phase centers. From this phase center, suppose if you are making another transmission is happening in the center of the array, and reception is happening in the same 3 segments, and correlate this signal from each one of it, antenna 1, antenna 2, antenna 3. You do a cross correlation analysis, and finally you are deriving all the components from that. So this is a study because it has gone into little details to look inside, because morning we are discussing about antenna and antenna theories related to how the important it's the patterns which you are generating it. Probably when you are getting into full interest can be discussed a little more. So I don't want to come inside, but there is a possibility for this radar. In fact, the ST radar now we have in Haringata can do that type of jobs, because that is having all the receivers. We got it and it can be done. So there is all possibility here to do the research, including NARL also, plus Haringata is giving you an opportunity to do a lot of research, subject of your interest. I am not talking about which one, you are not pulling it. You can look inside that opportunity exists either in signal processing, antenna point of view, understanding antenna, and how do you apply that antenna all theory, because it's not the design which we have done it. Actually this design, this experiments are conducted in a Japanese system. We are going there and looking inside the data which comes from the array, which is having 25 channels, same as this configuration what is Haringata is having and NARL is also having. You can think about it, experiments, what you have learned in your curriculum, you can practice it and look inside that on how it is going to come. Then look inside atmosphere and all its applications and deriving all parameters, what is happening in the atmosphere or in the climate, what you are looking inside, or probably that in the interest and people asking about climate change and all other problems. Look inside. Opportunity exists here, multiple radars in hand, and technically as well as it is a challenging studies. Many people have not done it. And many people also not looked into that one, what are the things we can do it. This is what I am trying to give a glimpse on this one. Probably look inside, what you can do it, still it can be explored. First picture he has shown, director has shown about 1974 Woodman accidentally found when he was looking ionospheric data. Still, after how many years? We are still doing lot of research in the same area. For us, the radar has come up in the last 30 years back in Gadangi. Still we are, and a system, and you can see that center has grown into such a big level and it become an international center for studies of this kind of things. We have grown to that stage. Earlier we don't have anything there. What you are seeing is a beautiful picture of all panoramic views. We have come with only, when I am first person joined there, it is only having mud. We created there. So you are the people to look into the system. Tomorrow what are the things we can do it, further explore it, further make it, what we can build it the system for, at least for our country also, that's very important. We have to grow, and we are growing, and we are making, first time when we are talking about the radar system also, we don't have radars. We have built it, we are made it obsolete component replacement or the modifications, and finally it is now come as an active phase array system there. These are all happen over a time. Still can be done. That's what one glimpse I am giving it. It is not studied this way. We can do it and look inside, and it is having a lot of application which cannot be done with a normal DBS, but what we can do it with the SA or the next level post beam steering when we are talking about it. So it's only just want to give a glimpse of it. Lot of study can be done, lot of ideas can be created, which you are not able to do one kind of mode of observations, but you can definitely look inside and get into the subject and study part of it. Yeah, I am just skipping all these slides because paucity of time, and I may not be able to explain in detail. Otherwise I need at least one of my file to clear it. At least one day I want to sit with you and interact with you and talk about it. So that we'll take it up later, and we'll how do we find SA parameters or space antenna techniques, how do we derive these wind parameters will be taken little later. But you can see that one, finally I have to get same wind information from any technique I am using it. Otherwise it is meaningless, correct? Two different techniques is used, finally two different signal has come, same atmosphere. Nobody will accept me. So you have to understand that is the pain in with us. How do I get it into solutions which is supposed to be like that only, that you have to be careful. That is what people, those who have done little and Hamiltonian mechanics and Lagrangian mechanics, both are deriving into the, starting is the same, in between they deviate and do totally philosophically totally different mathematics, finally again then join and say that both are correct. This is the world. You can also prove it in the same way. I am also right, you are also right. And you can bring more information in between what I am doing it, and it is more methodical or correct it also. Look into that point. Okay, it is because so much, in signal processing, in computer science, opportunities exist with this radar itself. It is not that only atmospheric science can do it, but atmospheric science is the prime component. That has to, all studies should lead into the benefit to the atmospheric science research what we are talking about it. But in between, community will be there with atmospheric research is talking about it. But in between there is a big chunk of things has to happen to get into the final result, and you make it more and more refinement. Our result to the estimations or anything will be less error and predictable in a better way, and we'll get a better result out of it. So these are the radars, beautiful radars across the world. We will add very soon our hiring data also. We have so many radars, which is I'm talking about the phased array system point of view. That time, but now NARL is also fully phased array in that aspect. That will also add it. Wind profiler also, all other things are adding it. So can you come next? Go out. I will take 10 minutes and close it, but the topic is for a long time. Not that one, last one. Yeah. Yeah, so far I think this subject is hardly touched in the world itself. We are talking about it. We have beautiful results also. A study which is carried out, I'm talking about a new approach. New approach in sense, you have so many systems or so many methodology or whatever instruments are available to derive all these winds. But there is one approach, again you can think about it. And this is the class of frequencies. Okay, I will skip this one because I need at least 5 to 10 minutes to talk about it, but I will skip for this time why these frequencies are very important to us. We are covered everywhere. We exist everywhere for the atmospheric community also. So that is very important. So let me go outside, little fast. So this is what we are talking about it. Beamforming and steering. We are doing beamforming there also. But that beamforming is well planned. In the beginning itself planned, you have to do it, you should have a hardware for it. But here the beamforming need not be planned at all. You are planning after a sleep is over. You have the luxury to do that. So if that is there, I am sure that you will go, but you have to pay a little more for that one. Your computation load is very high, so prepare for that computation to take it in your hand. That is what important here. So as he was explaining that one, when you are forming the beams, normally what you do, phase shifting. Each one goes through different phases and finally sum it up in one side and make a planar wave. That is a simple principle in the beamforming. So here also we have different phase shifters are used in principle in the hardware, or in the new generation system probably that each line can have its own DDS or direct data synthesizer, where that generates its frequency component with a phase shift independently, need not have a hardware inside of it. That's what new technology talks about it. But it is a costly business. You can still do that one. So what we do, when it is going to each line or each element is put it with a 0 degree phase, you can see a vertical beam is there. Now if I tilt it little bit, tilt the 30 degree away from my vertical component by totally putting the phase shifter values. That phase shifter is digital value for me now. What we have to do? I create a beams or I transmit with the vertical beams. I have to put it inside a receive beams within the transmit beams, tilted beams, and I receive the data. I think one chart may be there. Yeah, this will tell you this process. I have transmit beams. This is what I transmitted. I received with the same array. All components are independently digitized and taken back. Instead of doing it, it is in the vertical. Post facto, I apply my phase shifting onto each line which the signal is received. So this is an opportunity again exists in this radar now. All the radars, we are bringing it up. When we have started, we have only single channel to do it, so we can't think about it. And I have not seen across the world, even people are having multi-channel receiver system, they have not come out with a good result out of it to see that in 20 kilometer coverage. So, but that is a possibility. So look inside, but range of observation has to be done. Motivations, lot of things you can do it. What conventional system or DBS techniques are not allowing to you. Even for atmospheric observation point of view, it is very essential for fast changing. What he has raising that one, look this side, look that side, look this side. We presumed in the beginning that one homogeneous environment, but that is not the case all the time. Most of the time, system is not like that. We can presume that one because I don't have it that kind of system. I will presume it, average it out, and I got the global behavior, but not in the deterministic way. I can say that one, that is correct. So if you want to do it, you should have a sophisticated system in backend. Now you people are getting an opportunity to do that one. Look into that factors, what people are, your ancestors have done it, what changes you can look inside when you are doing like this. These observations will help you. What we get it in the pointing beams in multi directions and get it in 5 minutes one scan, say, this will do in 30 seconds. Imagine that temporal resolutions you are improving, and this 30 seconds you are not switching the beams in different direction. You are already illuminated the entire area. From there you are extracting the informations. So it is uniform at a given instant of time. What is happening in that side, this side, everything is retrieved from a single call. Whereas the other one is done in a Doppler beam swinging method. This is happened in 30 seconds. After that 30 seconds it goes there, goes here, like that it rotates. Here in 30 seconds, entire transmission is happened, collected the data within that time, and beam is formed post facto after your convenient time, if it permits you. Sit and do it, see the performance. There will be a lot of change. And it will not allow, because a simple example which is I am not going into much detail because it's so much of detail. This is I have done in the study, which is almost similar system is here now, but this is done in 2004 time. It is a Japanese system, Mu radar, one of the best system in the world. I can tell you, don't feel bad about it. Indians also having system now in a best system, but that is one of the best system. Mitsubishi Corporation has done this job, but it is one of the best system. Configured, what I am telling, 1986-88 period, they configured the system in this one. When we are doing it now, maybe that earlier morning talk, we are done our first radar with the 5 agencies together, funding. That was the reason. But now India is not like that. You got a golden opportunity. Look into the programs and projects. Aim big. Aim big. Project bigger programs. Project it. It's a novelty. People are there to fund it. We want that kind of programs to come out of you people. Think about it. Study for that one. Don't leave it. Just like a curriculum only you are doing, you will see only with an equations. But look into that. What are the things you can do it for the future? And you have sample system in hand. This you keep it as a sample system, even though it's sophisticated. You think about it bigger way. What you can do it, but you have to project it in a very big way, saying that one, what advantage I am going to bring it out. People are not going to give you simply like a bag, okay, take the money and you do enjoy it. That is not there. So aim for that. What you can do, what is not done earlier, we are doing it. Even this one is done. I have went into the 1987 system. I went to 2004. I could do it. And these all things are published in the IEEE. How the possibility is happening there after 30 years. And this is a system which is open to the international community. Everybody can go and do the experiment and conduct, and they will spend 4 months, 5 months in research programs, do the experiment and come back. So that is what, you have the opportunity, you can do it. And that is what we are calling you here, and sit and listen and look back, go back and see that one, I want to grow in that area. That is what you are getting opening up now. And we are all the way coming and advocating for that. Please look inside very positively and try to do something which will benefit you, benefit the country. This is the system, 25 channels, how it is configured. It's showing that one. I just go to the result only directly. Later probably, a lot of, yeah, I was talking about, it is not easy method, but at the same time, it is a doable things. It is done already, so what we can do it. So totally we are going with a simple beamforming techniques, purely mathematical numbers, crunching with mathematics. Your computer does the job, only you have to think how to do that. And that will give you a lot of happiness to you that, okay, I am getting it out or not. And lot of different beamforming techniques, each one is having its own advantage, and you can project it. So without looking much on this one, because you can see that one, it is totally a matrix-based computations, getting into its transpose matrix and determinants components and covariance matrix. That are all going to come. Wherever you work in advanced scientific and technical programs, these are the techniques now doing it. So you can do here also. And it is giving you the results what is expected. Very important to us. Many people are not getting inside because of some complexity is there, but you have to take the challenges and come back. What it means actually, 30 seconds of time, you can retrieve the entire information. It's very important when you are looking at convective systems. Because the entire field is, wind field is changes in the three dimensions or the three or four, 5 directions or 4 directions we are looking, everything gets changed. So when it is changing, the presumptions we have kept it for the DBS techniques, whatever wind you are retrieving from there by a simple method what we are shown in the beginning, is not holds good. So if you want to get it, that is very important. And there are some of the atmospheric parameters like momentum flux or something what you are talking about. It is also believes that one, that change should not be there. But that is not the nature, is not supported that way. But we presume that one, okay, granted, let me do it. But you can do it now. Everything is available in one shot. You can get the information and retrieve the information and talk about the atmosphere, what is happening there. And people are looking for it, what changes are happening in the atmosphere, like people are asking about the chemical changes or ozone or whatever it is there. All are influencing your life. Directly or indirectly. You may not be feeling that one, but it is influencing day by day, and we are on endangered species very soon. So we have to act. This is the only way you can say that one atmosphere is getting into problems. Even if it's minuscule level, you people are projecting it, that is very important. So I am not getting into mathematics point of view because analysis is having a lot of importance to see. You can get complete radiation or the wind pattern in one shot. 30 seconds time or whatever you talk about it. You can see this is the velocity informations which is extracted in 30 seconds. All the regions of velocity. This techniques only will help you. Other one is time-based analysis. We don't know what is happened there. So you are getting a positive velocity and a negative velocity opposite, which shows that one your retrieval technique is correct. And this is the various components which is derived. And we just touch the only whether again this matches with the rest of the factor observations also. You can see here entire velocity is extracted the same way that what we normally use to get it from the other method. If this is not satisfied, you cannot call that on my mathematics or model which I adapted mathematically inside by a post-beam steering concept, which will not work out. You plus to accept it. These are all IEEE papers. You can probe it and get it also and read it more. Probably when time permits, we have just given some examples about the when a large convective system prevails and observation is conducted, whether it matches to us or not. So these are the observations which is available, and you can look into precipitation also, because atmosphere is having everything to you and to enjoy for you, everything is given. You can look inside, you can get a lot of the information about the atmosphere by looking into systems of various nature. That's what NARL is having, is showing something around 50 different atmospheric observation instruments. Not only atmosphere, it goes into now ionosphere, space and other things also goes out of that one. So it's a golden opportunity for all of you. I'm stopping here. Probably I may get a time to explain much more details when it comes to some other time. Otherwise, fine. These are all talking about some of the observations which is never possible the other way we have conducted. Anyway, I'll take it up. You can take up. Come on. Yeah.
So if there are any quick questions, Dr. Anandan will be happy to take that. In addition, he will be present tomorrow as well at Horinghata for the hands-on exposure of the students. So, yes.
See, most of the work he has, whatever he has shown, actually he has done himself, either using Gadanki or at Shigaraki. Shigaraki means Japan. Okay, so they are quite involved, but you can actually learn a lot of things, that what kind of parameter you can extract, very rigorous, technique. What we say, we are measuring like this. This is what it is. So we have to make the system robust, because a priori you do not know what the atmosphere is. Correct, na? See, you tell me what is the difference between the phase of 40 degree and 400 degree. Can you tell me the phase 40 degree and 400 degree? Huh? 40 degree phase, draw a sinusoidal curve, 40 degree and 400 degree.
They are same thing.
Huh? How do you know it is same thing?
Sir, because for a complete, if I consider a coordinate axis, then 360 degree and then 40 degree
40
out,
degree,
and then
isn't
40
it?
degree. So
Now, if you are measuring 40 degree, how do you know it is not 400 degree? What you measure may not be correct.
yeah,
So, by bringing in, this kind of technique, improvised technique, we will be more sure about what is the truth. Correct, no? So, we are trying to understand what is the truth, what drives atmosphere, what are the physical processes which are governing the atmosphere. This is what we are trying to know, isn't it? Through observation, through computation, through modeling, various ways we are trying to know and consolidate, this is what it is. Correct, no? Today also people are challenging, or verifying rather, the Einstein theory of relativity. Those who are familiar with the gravitational wave, you know that this is one of the things they want to test, the Einstein special theory of relativity. Correct? So, when Einstein did it, how many years are over, but still we want to do. What we want to achieve, I do not know, but we want to do. Human beings are like that. Okay? So, what I am telling you that a lot of this thing is there, he is around. I am just telling it, Anandan will say, is loading me. The thing is that those who are interested in signal processing, very high quality signal processing, it can give you a professional career, wonderful professional career in the country. You can directly contact with him, he has done work, you can take his guidance, possibly join PhD program under his supervision.
I missed one presentation just to shoot you back. Normally when we look the signals, everything looks, you don't understand, especially atmosphere. It's a very gambling area. Why that word is used? In fact, we are touching an unknown area where there is no idea about it. How do you characterize? That's one of the signal in the beginning that we talk about it. When in the signal processing system, it's a system of unknown. How do I get a transfer function of that one? If I am talking about people, those who are probably a paper is touched about signal processing transfer function and all. Don't worry about if it is, don't understand also. But if you do find out what is happening in atmosphere, how do I characterize that? There is no direct method to do sometimes. Even I retrieve the signal, it will not reflect you that what process has undergone in the atmosphere. I talk about that, even distributions we talk about it, Gaussian distribution, Rayleigh, chi-square, or any number you put it. There is so many things. When it comes to weather signals, we talk about Rayleigh, gamma, all kind of logarithmic distribution, everything is there. How do I know that one, these are the distributions there? This is an indirect way of looking into the mathematics point of view. How do you say that when my waves are going there, whether it is interacting in a linear way or non-linear way? Again, you can put it back into your signal processing and probabilistic theory, statistical approximations, and you can get it. That is not, I don't have positive time, I am not raising it, but those who are interested and seriously looking inside, still can look inside. Papers are available either my paper or the different people paper, but I may be there in the atmospheric community, but there are people, those who are done in the different levels and can find out. Thank you.